Good morning, everybody. Welcome to this new seminar. Today we will have the talk by Dr. Maria Kouttoulaki from the University of Leeds in UK, and she will talk about the VLTI view of massive young stellar objects. So Dr. Maria Kouttoulaki, originally from Greece, did her PhD at the Dublin Institute for Advanced Studies in Ireland, working in the field of star formation under the supervision of Professor Tom Ray, Professor Antonella Nata, and Professor Rebecca Garcia. After her PhD, she moved to European Southern Observatory headquarters in Aachen, in Germany, where she joined the group of Professor Leonardo Tesli. And now she is a postdoctoral research fellow at the University of Leeds in the group of Professor René Outmeyer, working on young stellar objects using infrared interferometry. So thank you, Maria, for accepting this talk, and the floor is yours.
Yeah, thank you for the nice introduction. Before starting, I would also like to thank this VLTI program for this, giving me this opportunity to be here this month. It was really great. And also to Rebecca Diane, because she was really host this past month. Yeah, so I think today I want to talk about a VLTI view of young stellar objects. Here are a few of my collaborators that are in Chile and also in Leeds. Yeah. But first I would like to start also why massive young stars are important. First, I want to show this first schematic image of young stellar object formation. And this is mainly for low mass stars, but we have the molecular cloud. When we have the collapse of the molecular cloud, we have the creation of the protostar. And as we go through the classes here, we have the creation of a disk, which is important for transferring the angular momentum. Some cases we have some jets. In these stages, of course, the source is not visible at optical wavelengths. And we can really observe them at infrared, mid-infrared, or radio wavelengths. But as we progress in time, the source becomes optically visible, and we can observe it, and we reach this stage, basically, which we have a disk. Some cases we have a jet, and then we have also, we might see planets, and we have the standard picture of what we see on class 2 and Titori Herbig stars, so low mass stars, intermediate mass stars. Of course, depending on the mass of the star, if it would be a low or intermediate mass star, or if it would be a high mass star, the evolution and the depth, of course, will be different. Massive young stars are really important. They are among the most influential objects in the universe. Because their birth, evolution, as well as their death as supernova strongly influences not only their immediate environment, but also their chemical and dynamical structure and evolution of their host galaxy. Although these stars are so important, there's little that we know about the formation. In order to understand how these stars are formed, we need to go in the earlier phases of star formation, the so-called massive young stellar object phase. We're mainly talking about masses more than 8 solar masses. They're still undergoing accretion. They're really highly embedded, so we cannot observe them at optical wavelengths. So that also makes it more challenging to detect them. They're short-lived, especially in comparison to low mass stars, but also they're quite rare, not as frequent as low mass stars, and also really distant, like several kiloparsec away. As I mentioned, during the formation process, we have the creation of the disk. And the disk is really important, both in low, but also high mass stars. And this is mainly because the disk is the main feeding mechanism onto the star. But also, in the case of higher mass stars, that's also in both cases, that we can have the detection of companions, multiple system planets. But the really important thing is that it helps us to get rid of the excess angular momentum. Also, the disk really self-sheets against the strong radiation that massive stars have. And also, this is one of the questions, how they can become so massive, because they need the radiation to escape. And when you have a disk, it could escape in a perpendicular direction to the disk, which can allow further inflow and then have and be able to basically form a more massive star. If we go a bit, having a more closer look how a protoplanetary disk looks. So this is the case. So we have the central source in the middle. Then we have a gaseous disk around it, and this is mainly because the dust cannot survive more than 1500 Kelvin. And then as we go further away, we're forming a dusty disk going up to 100 AUs or even 1000, depending. This is more for a low mass case, so we have to extrapolate for a massive case. And depending on what we want to study, of course, we need to go to different wavelengths. So, for example, if we want to study more of the dust or the outer part of the disk, we need to go to sub-millimeter, millimeter observations. But as we want to go further in towards the star, we need to go to near different wavelengths, but also we need higher angular resolution. So here I just want to show an example of HLTI with ALMA, and basically to probe the accretion and ejection processes that are taking place in order also to understand the formation of these massive stars. We really need to go to distances of up to, like in the low mass case, up to maybe 1 AU. And in order to do so, we really need high angular resolution. In the case of this picture here, this will be the blob that we see unresolved here at the ALMA images. So the only technique we can use to really probe these small inner regions of the disks is to use infrared interferometry. And just to do a bit of a short introduction, so you can follow in the rest of the talk, we know that the resolution is dependent on the diameter of the telescope. So, for example, this is VLT and VLTI at Paranal in Chile. So if we take the UT telescopes, which have a diameter of 8 meters, at a distance of 100 parsec, which is usually the closest star-forming region, that would lead to a radius of 6 AU. But as I mentioned earlier, especially in the low mass case, we really need to go further in. And in order to do so, we need to use VLTI in that case, but this is the main part of the talk, which is the VLT interferometer Paranal. So you can either use the 4 telescopes, the UTs, or the 4 smaller telescopes, the auxiliary telescopes. And you can go up to, now this has been extended, so up to 200 meters. And basically the resolution is no longer dependent by the diameter of the telescope, but is dependent by the so-called baseline, which is the distance between the telescopes. In that case, would be 150 or 200 meters, which will allow us to reach millisecond resolution, which is needed to probe these regions. Unfortunately, the case is not as simple as we do with radio interferometry. Here, we need to manually combine the light of the telescopes. We have a lot of losses, but also we don't have phases. And this mainly because the atmosphere changes very quickly at near different wavelengths. So basically, we have some corruption. So we have other quantities that have been working. So basically, we'll be working in the UV plane. And 3 quantities that I'll be mentioning along the talk is, for example, the visibility. The main thing you need to remember is that the visibility is the contrast of the fringes and mainly gives you an estimate of the size of the emitting region. Visibility is normalized value that we use. So 1 is a point source, 0 is something completely resolved. And then instead of the actual phase that we use at radio interferometry, we can use the differential and closure phases. So the differential phase is the photocenter shift of the line with respect to the continuum. And closure phase, we need at least 3 telescopes to have a closure phase, and that can give us an idea of asymmetries in the circumstellar environment. Here is just an example of a closure phase and what it means. So for example, if I have a disk and I put my baseline along this way, basically the illumination I get from here and here will be equal as it is here, like a phason, for example, as we see it here, and that would give us a closure phase of 0. But if for some reason it's inclined or something else is happening along the direction that we're putting the baseline, and we have an uneven illumination, as we see here, that will create a non-zero closure phase. And this is a really powerful phase that we can use also for imaging, but also to understand the asymmetries in the circumstellar environment of the object we've been studying. To go now to some results, I want to start a bit with the dust, and then I'll move to the gas. Here on the left, I just want to mention that so far there have been quite a few studies in the case of low mass stars and intermediate mass stars, especially after the VLTI gravity, so the second generation interferometer that has been a few years now that's in use, that operates in K-band, which I think I didn't mention before. So this is the first statistical survey in the K-band that happened in the case of intermediate mass stars. And here is just a diagram of the ring radius versus the luminosity. And all we can see is that the ring radius scales as the square root of the luminosity. That's something that has been proposed before as well, but this is something nice that we see here as well. Of course, there is a bit of scattering, but more or less the trend is similar. This was the first step that was tried to be done, and the second step was to do imaging. This is something that is really quite challenging in infrared interferometry, and that's because you only have 4 telescopes. So in order to have an image, you really need a lot of information, a lot of observations in order to fill in your UV plane. So to do that, you need hundreds of hours, especially for a survey like that, like here. So this is the first image survey that was done in Herbig stars, and this is in the H-band. And it was really nice to see all these different substructures and structures that we see in Herbig stars, and they're not just as uniform as we also see with ALMA as well. And although all this has been done in the case of low mass and intermediate mass stars, in the case of massive stars, not much has been done so far. This is actually the first image of a massive ancillary object here that was done in 2010. And since then, this is the only image that we have so far. And this is actually the first detection that massive stars can also have disks, because this is something that from theory, it had been predicted. And this is something we're expecting in order to have more massive stars. But this was the first detection that would actually say, look, there are disks around these stars. So that shows that also image reconstruction is really important. And this is something we're trying to push towards, which I'll mention briefly in the end. And also it shows that there are wraps, that there are rings, there are self-shadowing, there are a lot of structures and a lot of work to be done so far. But to mention a bit more about the case of massive stars, and although this is the only image so far, there are quite a few things we can do with the observables, as I mentioned. So here is a similar plot like the one I showed you before for the Herbig stars, and we can see here Titori and Herbig stars in the same plot, ring radius over luminosity, but then also we see here the massive stars. And these are all direct detection using gravity. And this is the first time that we can actually see this trend, and also shows that the inner ring, the inner region of the disk also scale with the square root of the luminosity, independently of the stellar mass. And that was really nice to see, because until recently we could only have that information for this part of the disk, for this part of the evolution, but not for the higher mass stars. Of course, this is only a sample of 6, and we really need to populate this area, and this is what we're trying to do, but this was a nice result to see. There are other tries that are trying to be done, and also this is mainly to have a more of a multi-wavelength study. And this was done by Frost et al. That it was a really nice study of 8 massive young stars using MIDI. So MIDI was the previous interferometer using a 9 band, so around 12 micron, and also the zero comics images at 20. And by fitting simultaneously the ACD along with the interferometric observables, they could fit the visibilities. And what they saw was that, first of all, that the massive disk outflow evolution follows a similar path as low mass stars. But the other most important thing was that you could see substructures. So they could not fit, quite a few of the data could not be fitted unless there was some kind of substructure or asymmetry. And this is something that needs, of course, we need further data to confirm that, but also try to image that. Going towards the gas. So bracket gamma. Bracket gamma is a really bright line at near infrared wavelengths. In the K-band, it's really bright line in young stars in particular. And so far, this line had been associated a lot with accretion, but a lot of studies has actually shown that that's not always the case, but they can also have a contribution from a disk wind or the base of the jet. In the case of more low mass stars, in case of T-Tauri stars, yes, it has been shown that probably it faces the magnetospheric accretion columns, but in higher mass stars, it's still not clear if it could be a disk wind or a jet or just facing accretion through the disk. So, so far all the studies have been done with interferometry that have been focusing on this line because this is the main line we actually see. A bit further, I'm going to focus more on other lines that I would like to show you that there are other lines we can use. But just to see here, this was the first result that with interferometry, we could directly resolve the inner disk of TW Hydra, and that we showed that the bracket gamma line traces the magnetospheric accretion columns. And this was really a nice result to see because so far, of course, there was the theory, but that was the first direct detection. But as we go to higher mass stars, for example, this case here, we could this is just an example how we get the results from interferometer. So we have a normalized spectrum, we have visibilities, and this is the closure phase. So you see that, for example, our visibilities are around 0.2 here, which basically shows that it's almost resolved. And then as we go along the line, you can actually see a bump here. And this bump here shows that the visibility of the line is actually different than the visibility of your continuum, which is in this case is your dust. And by doing some calculations, you can actually remove the contribution of your dust. And you can see here the visibilities that correspond only to the line emitting region. And you can actually see that they're much higher than your total visibility line here, which basically shows that your line comes from a region that are much closer to the star than the continuum, like your dust. So within your dust sublimation radius of 1500. And then basically by fitting geometric models, but also by fitting more complicated modeling like understanding if it's in a Keplerian pattern or not, of course, by using the differential phases that can help you with, you can actually say where it's coming from. There was not a clear detection where it's coming from. It's still much further away than tracing magnetospheric accretion, for example, but probably could be tracing a disk wind. And this is another example that I want to show for higher mass stars. And this is radius of bracket gamma over the continuum versus the luminosity. One here as the continuum, and you can see that in all these cases, the bracket gamma line is much below than your continuum. Of course, it's much more extended, which probably, because we didn't have enough information, differential phase, we could not really say if it's actually coming from the base of the jet or the disk wind, but it's one of the two. So we can see here that there are three different cases that could be tracing accretion, could not be tracing accretion. But if we want to really go to a tracer that really traces the disk, an ideal tracer is actually the CO bandhead emission at 2.3 micron. CO is quite abundant in the case, though at 2.3 micron, the CO overtone emission is not as, we don't see it as often. So for example, in the case of T-Tauri stars, I think there might be 2 or 3 detections. In the case of Herbig stars, more intermediate mass stars, we have around 17%. And in the case of massive young stars, around 20%. So it's difficult to observe, but when it's observed, it's an ideal tracer to help us understand the inner gaseous conditions of the disk. Here, I'll just show, for example, a high spectral resolution spectrum with Kraus, so that's around 80,000 spectral resolution, and we can see the first bandhead at 2.3 micron, and you can see all these wiggling here, which are the individual J components that you actually spatially resolve. So, for example, this is just again the spectrum here, but here I can just show the P branch and the R branch of the overtone emission, and this is just to show that by creating an LTE model. So like having a ring or a disk in LTE conditions, we can actually fit this spectrum and extract information like temperature, column density, and especially when combined with interferometry, can actually give us also the geometry of the system and becomes more of a powerful tool. And this is what we try to do. So this is a great example of CO overtone emission using gravity. This is 51 also, it's an intermediate mass star in this case. It was chosen as the first candidate when we observed with gravity, because you can see here all this wiggling at differential phase signal, which basically shows that the photocenter shift of your CO emission is actually quite different from that of your continuum. So it comes from a different region. And we can also see here, the scale is not perfect, but along all the band heads here, there is a bump. And that, the first step that you can do with this data, with your visibility, and also an important thing to stress here, you can see that the total visibility is between 0.8 and 0.9 for quite all your baselines, although you go up to 120 meters, which shows that the system is quite compact, actually. So in these cases, the first thing you can do is you can remove your continuum emission and fit this CO emission and see where it's coming from. And this is the first step here. So we see visibility versus spatial frequency. This is just to have an idea, it's just the baseline over the wavelength. So as we go to further spatial frequency, basically we'll go to smaller scales. And here is just a 2D Gaussian fitting over your visibility points. And this is the way you can actually derive a size of the emitting region. And here we can see your continuum, and the red points here is the CO. And what we saw from there is that the CO is quite compact. It comes from a region that's closer to the star. But the main problem here is that although we go up to 120 meters, this is not enough to really have more information of the tail of the Gaussian. It stops quite here. As you go to bigger wavelengths, you expect basically your visibility to go to 0 because you spatially resolve everything, and that's not the case for this source. So what we tried to do was here is took a spectrum, fitted an LTE model of the CO, like a ring in capillary rotation, extract temperature, column density, V sin I, and then from there, by having your LTE model, so you have your model spectrum here, you can actually create an intensity map. So this is the case here, we can see. So this is an intensity map for a blue shifted part of the line, the peak of the line, and the red part of the line. What you can notice here is actually that the CO doesn't behave as a normal line. And that's because you have the different J components that, especially when you have the Keplerian broadening, there is a lot of blend of the velocities there. So although the blue part here, which is actually the shoulder that you see in the first band head, gives you the actual, you can see the velocity formation is expected. As you go to the peak and the right part, there is a huge blend. Nevertheless, by having this, the next step to do would be you need to compare it with basically your differential phase signal. And in order to do so, you can actually calculate the photocenter shifts. It's basically like doing spectrometry. So instead of having one slit that direction and the perpendicular or whatever to do your spectrometry, you use your baselines basically. And then this is the result. So basically from here we actually calculated the phase of the line, which is the different colors here. And then from your model, you calculate the shift, the photocenter shift, as you expect from this model that you have used. And you can see here the result. And of course, what we expect is we expect to have the maximum shift along the major axis of the disk and the minimum shift along the minor axis of the disk. And this is what we observe here. But the important thing here is, although the system is quite compact, by doing this, you can actually have an exact location where the emission is coming from, but you can also have an estimated inclination, position angle, and then by fitting, you also have your conditions there. And basically what we find from here is that the CO is actually coming from a region of 0.1 AU from the star, which is something quite surprising. I mean, we expected that the CO needs to be, of course, inside the gas, but for a star like that, which is around 4 solar masses, there needs to be something there basically to shield your CO. Going forward though, here, this is an example of a massive young star, and we did similar things. So this is just showing the first year bandhead emission. You can see here a much clearer bump on the visibilities as you go along the CO line, which again indicates that the CO is coming from a region that's closer to the star. And what's important thing from here is that, as a few of you might know, is that massive young stars, of course, as I said, they're really embedded. They're quite rare, so it's much more difficult to observe them. And of course, because of that, we also don't have enough information or information we can trust about their luminosity or their mass. And this is a case where we actually managed to calculate the mass of the central source, and that's thanks to the CO banded emission. So again, we fit it with an LTE model. So we have a ring in LTE conditions, and then from there, because we also have the VSI information, we actually calculated the central mass of the source. Of course, as I mentioned earlier as well, and in this case, there is a lot of uncertainty on the model in terms of the spectral resolution. So this is something because gravity only has 4,000 resolution, but as you go to further wavelengths, as you go to further and higher spectral resolution, you can distinguish the individual J components, which are basically needed to have a much better model. And this is something we're trying to do, and we're pushing towards having high angular resolution and high spectral resolution observation, combine them so we have a much better result. Here's another example that I've been working on now. So this is another higher mass case, and we can again see the 4 band hits here. We can see again the CO emission here, and also we can see a huge differential phase signal. That's also what is nice here. It's also there is a CO closure phase here, so you can see that you have a global closure phase that is around 20 degrees. So there is some kind of asymmetry, but also you have an extra asymmetry on top on your CO. So by doing a similar thing, by fitting a 2D Gaussian again of visibility versus spatial frequency, we can see here that your lines like your bracket gamma, sodium, and CO are all more compact than your continuum, but you can actually see that the continuum is quite extended. Your CO is kind of extended. And the same goes for the sodium. Sodium is also another tracer that I'm going to mention in a moment. And this is not surprising to see, but there are indications also for fundamental emission, but also other cases that we see that maybe the CO is not only tracing the disk, but maybe that could be coming also for maybe some kind of outflow or somewhere more extended that we were expecting, especially in the case of higher mass stars. And a thing you can do by having this differential phase, as I mentioned, apart from fitting the modeling, you can also calculate your photocenter shifts and project them on the skies. And that can actually gives you an estimate of exactly where it's coming from. For example, here, what is interesting and is still puzzling with trying to understand is that you only see emission of your CO towards only one direction. And you see some emission there. So for example, this is the disk, and this is actually the outflowing direction. So we're not sure exactly what's happening yet there, and something it's in progress, and we're trying to understand what's going on, and also because we need to, I think, work a bit more on the closure phase as well. But just to give you an example of bracket gamma and how it looks when we do this spectrophotometry, this is another massive young star, which has been observed a lot because it's quite bright in the K-band. And here we can see the direction of the disk as green and the direction of your outflow. And you can perfectly see your bracket gamma aligning along the outflow. And that's basically the main, that's the only way you can actually prove just using your interferometric observables, if you have, of course, a differential phase, to prove where exactly the emission is coming from. Is it tracing the jet or if it's tracing the disk or something else? So moving on to a few more tracers, I want to talk a bit about the sodium and the helium. So these are tracers that are, especially also the sodium, that are accretion tracers, but of course, we don't see them as often. It has a bit of a higher rate than the CO, but still, so usually what we see is all targets that have CO also have sodium. But to specially resolve this emission is quite challenging, because also the line to continuum ratio is really important to detect some signal on your interferometric observables. Here's just an example of your visibilities again. So you can see that there is a bump here tracing the double peak, so the sodium doublet that we see here. And also here, this is the helium, and you can see if I would blow up, you would see more of a P-Cygni profile, and it's actually a similar profile as your the bracket gamma line that we see on this source. So here, by doing again a similar geometric modeling, we can estimate that actually the sodium actually comes a bit closer to the star than the CO emitting region. They're all both two tracers that are actually tracing the disk. We have bracket gamma a bit more extended, and then helium even more extended. So helium, we didn't focus too much on that because it's the only measurement actually that we have in the case of massive stars. Previously, with spectroscopic studies, we could associate this helium emission with accretion on here big stars. But here we need more information because we didn't have any differential phase signal. But what we can say, of course, is both the CO and sodium, they're all coming in this dust-free region. And here's another example, which is the same target as the one I showed you for the CO now. And this is actually the first detection of the differential phase signal on the massive young star. By doing, of course, this is the same plot I showed you before, that we see that actually the sodium is actually more extended than the previous case, and it has a similar trend that we saw for the CO, which is still a bit puzzling, but we also see some closure phase in the same case as well. This is just as a demonstration. This is a model image of the two emission has been taken, like extrapolated from MIDI towards the K band, and that shows that we have something quite face on, but also you can see a strong illumination here in respect to that, and this is basically what creates the global closure phase that we see. So I think just to conclude a bit, or some takeaway messages, I just wanted to show that there's a lot of improvement in also the case of massive young stars that has been done with near-infrared interferometry. We can really now especially resolve the disk of young stars, especially now with the developments that have been going on with VLTI, and especially with gravity, also the gravity plus that we have now. We have really pushed the limits to go down to much fainter sources, but also allow us with new capabilities of gravity to fringe track further away to allow us to really have a more of a to allow us to observe more of these massive young stars, because before we were really limited to the brightest sources. There are new tracers that we can use, and as the sensitivity is improving, we actually start to have these tracers like sodium and helium, and they're really powerful diagnostics in understanding and in tracing the star disk accreting / injecting interface, because it's still a debate. It's also for the helium a bit. And also that spectrometry is a really great tool, especially like if you have a differential phase signal, you can really use it to understand and trace where this emission is coming from. And just as next steps, because of course, there are a few things that have been done, but there are a lot of more things that we can do. The next step in terms of our group trying to go forward on this is to have more multi-wavelength studies combining HK and LMN bands, because that will give us an idea of having of tracing the inner disk from actually 1 or 1.5 micron all the way up to 12 microns. And this, and also combined with radiative transfer modeling, for example, can give us a much better idea of the dust and the conditions that are there of the dust, but also multi-wavelength imaging as well, which is something that we have something already going on. So we have a program with Gravity and with Pioneer on imaging programs, and that's basically the next step further to try to have images of these sources, because this will be a better way to understand exactly what's happening in the environment of these enigmatic objects. Another thing which I haven't mentioned at all in this talk is binarity. Binarity is really important because we expect for high mass stars to have a ratio of almost 100%. And this is something that hasn't been from imaging programs. For example, with NACO, it has been shown that it has maybe a 60–70%. In a mini survey in K-band, it had shown around 17%. So this is something that we're really missing information also for closing companions. So for that, to address this issue, we have a large program going on, detecting binarity with gravity. So hopefully we'll have some more results on that as well. And the last part, which I think I stressed a bit also during the talk, is the high spectral resolution observations, which are really needed for kinematic modeling. So now we've put forward to having And that's something we're actually already working on in the intermediate mass stars, and we're trying to do with massive young stars to have Paris plus observations combined with gravity and understand the kinematics, for example, of sodium, CO, of course, bracket gamma as well. So by combining all this data, we expect to have some better results. And with that, I think leave you to it, and I'm happy to take any questions.
Thank you very much, Maria. So now, Rosen, you will manage the questions, please.
Sure. Well, thank you very much, Maria. So now, does anybody have any questions here in the audience?
Thank you very much for the report. There is an important ingredient in the case of massive star object, which is the iodine. They are coming from the H2 region.
Yeah.
This observation can be seen between these kinds of emissions, also the post-blue area. Would you address this problem, or you have selected only massive stellar candidates without the ionized material?
Okay, so far it wasn't really addressing specific cases of massive young star. It would just be the brightest that we could observe, having or not having any material around. So basically, so far we're just trying to address with a bracket gamma, basically, if that could detect a jet, and maybe possible combine with spectroscopy or imaging to see if that could, or even ALMA or radio observations, just to see if there's a counterpart or whatever. But also in the case of the large program now, it just whatever can be observed so far. This is the main way we've gone so far, just because it's quite challenging to observe them. So that would be the ones that are more visible, basically. So if that happens to have cases like that, we'll try to address them, but it hasn't been chosen. The sample hasn't been chosen with that in mind.
Okay. Does anybody else have any questions here in the audience?
Okay, thank you for the nice talk. I have a general question for you, because maybe you mentioned at the beginning, but these examples that you have shown are pre-main sequence stars, or are they in the main sequence?
They're all pre-main sequence stars. So in the case where her big star, pre-main sequence. So they were all young stars.
So the idea was whether this is a really ionized area, because that was the second part of my question, whether you can actually measure also emission lines or emission line, I mean, forbidden emission lines. So do that for that.
No, so for example, in the K band, if yes, so only if it's strong enough that could maybe specially resolve something. So far it hasn't happened. I'm not sure if there might be some cases in main like it has been done, but the cases of massive young stars, no. What I've seen, I think, is maybe have H2 that has been specially resolved, maybe, but in a case. But usually the issue is the line to continuum ratio. So if it's not strong enough, either you have to really integrate longer to manage to see if there's something there you could detect. But so far it's usually bracket down because it's the strongest, and then all these other new traces we're trying to address just because we integrate longer and the sensitivity has gone down.
Any more questions here?
Thank you, There you show some images obtained with the infrared interferometric, but these are continuum data, right?
Yes, these are continuum data.
For your line data, you only show the visibilities. So
yeah, because so far
you don't have enough UV coverage, or
yeah. So this is in case of big stars, so intermediate mass stars. In the case of massive stars, apart from the 2010 image of the continuum, we don't really have any more images. Actually, there are a few coming now soon. So, for example, what we're trying to do, which we have some imaging programs going on right now at VLTI, is to address the line as well. So bracket gamma and CO, and try to do modeling of all the emission lines we detect there. The issue with the lines is that, of course, it's the UV coverage, which needs to be the same as your continuum. But also you need to integrate longer to have better signal to noise in order to have information, especially in the differential phase and closure phase, that you need this information to reconstruct your image. So this is time consuming, and also you need to have an ideal candidate that has strong lines to start with. Otherwise, it's more difficult to do it.
This is just curiosity, for
Yeah.
example, maybe, you know, if is any of these sources have been, I mean, you have the disk, so are they in the optical showing any bipolar structure, or just they are very faint?
Especially the massive young stars are not usually optically visible. We've seen that a few of the cases that we have in our sample to be observed now have Gaia magnitudes, but they are going down to 20. But usually that's not the case. There is a case that Ruben was studying actually that we had the HC image, right? But usually that's not the case to have, and that had the bipolar outflow, and he was studying the jet. But usually it's not the case to have optical images of these sources. Yeah.
Please, Andrew.
I have a question about the sodium line.
Yeah.
In some of the plots you showed, it was clear that for all the lines, the structure was more compact for continuum. But in any case, I saw that for the bracket gamma and CO, the structure was somewhat resolved. However, for the sodium, it was more compact.
Exactly.
Does it make I mean, does it have physical meaning?
What we think is that in the case of the CO, it seems to have yes, tracing the disk, but maybe tracing something else. That's why it becomes more extended. And we think that probably sodium is coming a bit closer to the star than the CO. But we have a case that sodium seems a bit more extended as well. But the issue is that so far we didn't have any differential phase signal on the sodium. And because the line to continuum ratio is so small, I think we're a bit on the limits to spatially resolve it. And maybe we might be seeing it a bit more compact, but maybe that's not the actual case. Because with the case now that we see the differential phase, it seems to be more extended, not from the CO, but more extended than we thought, at least in respect to the other case, which are similar cases. So this is something we're working on now, just trying to understand if it's actually physical meaning of it, or it has to do with instrumentation limit, basically. We don't really detect all the emission.
And you don't have the differential cases because, I mean, the signal to noise ratio is not
good enough. So we must have integrated longer, for example, if we wanted to see that, and or basically we need the UTs. If you don't use the bigger telescopes, with the ATs, we don't get any signal on these lines, especially in the differential phase. So we have one case that we have that with the UTs, but the other case was ATs and we didn't see it. Yeah, so that's something we're trying to do now. Yeah.
In this sense, there are any extended atmospheres, or there is a clear separation?
So they still have a lot of envelope gas around. So we have cavities, the outflow, and all the structure here. They're really embedded. But we're trying to trace the disk basically and go further in.
Okay. Well,
This is a comment. I was thinking that it would be great to constrain or to calculate the gas exclusion from and compare with the observation, no? Because it will put very strong constraints to the models. For instance, we know that these massive stellar objects are still surrounding for the dense envelope. So for the physical conditions of the envelope, it would be great to calculate the gas exclusion from, no?
Yes, so for example, the continuum that we get there is actually that dust sublimation front. So then you have exactly the radius where this is happening, and from there you can calculate a temperature, but also by having more data or more wavelengths, you can actually have a more radiative transfer approach and understand exactly the values instead of just calculating, okay, this is the radius, this is the temperature I'm getting. Yeah.
is there any other question here in the audience? Anything on Zoom? Anything see anything? So before closing the session, just an announcement that Maria will give also an informal seminar on Monday for like the principle of interferometry, just in case you got interested on the techniques for your own science, you know, for the galactic people, for the extragalactic people, for the planet people. I don't even know if that can be done, but maybe you want to try it. So Monday at 10 o'clock next to the kitchen, we will have like an informal session, plenty of discussion. So she will tell the few more technical things that she couldn't tell today. You are all more than welcome, please. Yeah, so let's thank Maria again, and thank you very much for being here.